Hey everyone, and welcome to this explainer. So, today we're tackling a question that sounds super simple, but is actually totally profound. What is Earth? We're going to take an epic spaceship tour of our home planet. We'll check out the mind-bending scale of our cosmic neighborhood, rewind the clock billions of years to see how this spinning rock was actually forged, and then dive deep underground and way up into the sky to figure out exactly how it manages to keep us all alive. Here's our flight itinerary for today. First, our place in space. Second, the birth of a planet. Third, a journey to the center. And fourth, our protective shields. Let's jump right in.
Okay, Section 1, our place in space, finding our cosmic address.
93,327,712. Yeah, that absolutely massive number is the precise distance in miles from the Earth to the Sun. Astronomers actually call this one astronomical unit, or AU. We're the third planet from the Sun, hanging out at an average distance of about 150 million kilometers. To really put that huge gap into perspective, light traveling from the Sun, which, remember, is moving at the literal speed limit of the universe, still takes about 8.5 minutes to actually reach us here on the surface.
But you know, we aren't just sitting still at the end of that light beam. 29.78, that is our incredible average orbital speed in kilometers per second. Think about that for a second. While you're just sitting there watching this explainer, you, me, and literally everything on this planet are zooming through space at nearly 30 kilometers every single second, all to complete a full circle around the Sun every 365.25 days. Now, it's honestly kind of hard for the human brain to wrap around planetary sizes, so think of it this way, straight from NASA's fact sheets. If the Sun were the size of a typical front door, Earth would just be the size of a nickel. Seriously, a tiny nickel. We're the largest of the 4 rocky terrestrial planets in our solar system, but compared to our host star, we are just a tiny metallic speck. So how did this nickel-sized planet even come to be? Let's move to Section 2, Birth of a Planet, rewinding 4.5 billion years. Our origins are absolutely dramatic. Before Earth even existed, there was just this massive cloud of gas and dust floating in space called a molecular cloud. Eventually, gravity pulled a chunk of this cloud together, shrinking and flattening it out into a spinning disk around our newly forming Sun. Inside this solar nebula, tiny little dust particles and ice started bumping into each other, eventually snowballing into larger space rocks called planetesimals. Ultimately, the Earth was born as a completely molten, glowing ball of fire, before it finally cooled down enough for its materials to separate into layers. This whole wild formation process, it took roughly 70 to 100 million years to play out.
The specific process that built our planet from the ground up is known as accretion. Basically, Earth didn't just magically pop into existence. It grew by slowly collecting and smashing into other rocky bodies. And as these smaller pieces constantly crashed into the growing Earth, all that kinetic energy created a massive amount of heat. It was this intense heat of accretion, along with some radioactive decay, that turned the early Earth into a giant swirling ball of liquid lava.
Okay, now that the planet is formed and cooling down, let's dive inside for Section 3, Journey to the Center, exploring Earth's layers. If you were to grab a giant shovel and dig straight down, you'd move through 4 main layers. We live up top on the crust, which is a really thin, oxygen-rich rocky shell. Right beneath that is the mantle, a super thick layer of hot, solid rock that actually slowly moves and shifts over time. Go even further down and we hit the heavy, metallic center of the Earth, which is split into the outer core and the inner core. Back when the early Earth was molten, all the heaviest metals literally sank straight to the center to form this dense core. And this inner structure creates an incredible contrast. See, both the outer and inner cores are made mostly of iron and nickel, but their states of matter are completely different. The outer core is this churning, superheated fluid. The inner core, on the other hand, is a completely solid metallic sphere. And the reason it's solid brings us to a frankly mind-blowing number, 9,800. That is the temperature of the inner core in degrees Fahrenheit. It is blisteringly hot. I mean, roughly as hot as the surface of the Sun. You totally think iron would just melt at that temperature, right? Well, it absolutely would, except the inner core is buried under about 3.6 million atmospheres of pressure. To put that into perspective, that's roughly the equivalent of having millions of elephants standing directly on your head. All that extreme pressure physically forces the liquid metal to freeze into a solid sphere, even though it's sitting at an extreme 9,800 degrees. Which naturally leads us to a pretty pivotal question.
If Earth is essentially just a giant spinning ball of superheated metal and rock, how does life actually exist here? Why aren't we all just fried by the harsh environment of space or, the massive heat right below our feet?
Well, the answer lies in Section 4, our protective shields, what keeps us alive. First up is the magnetosphere. Remember that swirling liquid iron outer core we just talked about? Well, as the Earth rotates, that fluid metal moves around, acting like a giant dynamo that generates a massive magnetic field. This invisible field stretches way out into space in a teardrop shape and acts like a literal planetary force field. It deflects the vast majority of harmful solar winds and cosmic radiation right away from the surface. And here's a fun fact. When a few of those charged solar particles do get trapped in the field and collide with our atmosphere near the poles, they glow, which is exactly what creates the beautiful auroras, or the northern and southern lights.
Now, right below that magnetic shield is the air we breathe. This is the exact recipe for our atmosphere, and it is perfectly balanced for life. It's overwhelmingly nitrogen, sitting at about 78%, followed by oxygen at roughly 21%. The really crucial takeaway here is that this exact mixture doesn't just allow us to breathe, it regulates our entire global climate.
But let's zoom in on that remaining 1% of trace gases. Argon makes up most of it, but look at carbon dioxide at just 0.0415%, along with teeny tiny fractions of neon, helium, and methane. Even though these trace gases make up such a ridiculously small fraction of the atmosphere, they are absolute heavyweights when it comes to regulating Earth's energy balance. They trap heat, ensuring the planet doesn't just freeze over. Though, as we know, shifting this delicate balance even a tiny bit can dramatically impact our climates worldwide.
Now, structurally, this atmosphere isn't just one big disorganized blob. It's neatly layered based on temperature. The troposphere, extending from the ground up to roughly 12 kilometers, contains 75% of the atmosphere's entire mass and is where literally all our dynamic weather happens. Just above that is the stratosphere, reaching up to 50 kilometers. Now, this layer actually gets warmer as you go up, making it super stable, with very little vertical mixing. Which, by the way, is exactly why commercial jets fly up here. They want to avoid all that tropospheric turbulence. And the main reason the stratosphere gets warmer with altitude is because of the ozone layer. Tucked nicely right inside the stratosphere, this specialized layer of gas acts as a vital secondary planetary shield. While the magnetosphere blocks out the solar wind, the ozone layer blocks harmful ultraviolet or UV radiation from the sun. This is what makes it possible for complex life to survive on the surface without getting instantly burned to a crisp. Of course, we really can't talk about Earth's stabilizers without giving a shout-out to our one natural cosmic companion. The moon isn't just a pretty object in the night sky. Sitting about 384,000 kilometers away, its gravitational pull creates our ocean tides. But even more importantly, the moon's gravity acts like an anchor. It actively stabilizes the tilt of the Earth's axis. Without the moon, the Earth would wobble completely erratically, which would cause wild, unpredictable shifts in our climate over thousands of years. As NASA beautifully puts it, Earth is the perfect place for life as we know it. When you step back and consider everything we've looked at today, the perfect distance from the sun, giving us liquid water, that churning iron core creating a magnetic shield, a perfectly balanced atmosphere armed with an ozone layer, and a moon that keeps our climate in check, you realize just how remarkably unique and fine-tuned our home really is. Which brings us to a final thought to leave you with. As we've seen in this explainer, Earth's precise life-sustaining balance took 4.5 billion years of chaotic accretion, fiery melting, and gradual settling to perfect. It's an incredibly durable planet, yet the systems that keep us alive right on its surface are remarkably fragile. Knowing what we know now about those delicate trace gases and the intricate layers of our atmosphere, how long can we keep it that way? I really hope this journey gave you a brand new appreciation for the rock beneath your feet. Thanks for exploring with me, and keep your curiosity alive.